This is 8A.2.2. We'll continue with the introduction of De Moivre's theorem. De Moivre's theorem is used to calculate z exponentiating with n, where n is an integer. We'll begin with a proof of De Moivre's theorem. The complex numbers can be represented in rectangular form like this: cosine x plus I sine x. And when we want to exponentiate to an integer value of n, De Moivre's theorem states that this is the final result, and the index or the exponent n can be introduced into this equation, where originally it was cosine x, now it becomes cosine nx, and originally it was sine x, it becomes sine nx. De Moivre's theorem also can be stated in another expression in complex exponential form. Now let us have a complex number represented with the modulus r and the angle theta, and this is the real part of the z, and this is the imaginary part of the z, and this is z is equals to r e j theta. Well, when we have z in this form, complex exponential form, De Moivre's theorem tells us that we can put this exponent n, where n again is only an integer, into the original form such that the modulus becomes exponentiating by n, and the angle is multiplied by n. So this is the form that we are interested in, and it is actually the same as the previous form. The only difference is that the r was 1 here, and that is why the r remains as 1 without exponentiating by n. Let us prove. In this proof, I follow Eddie Wu's video. This is the link. You can take a look. And there's Simple Science and Math, also trying to explain the same thing. I took a snapshot of Eddie's proof here, and this is how he goes about to prove De Moivre's theorem. RTP required to prove that cosine n plus I sine cosine theta plus I sine theta bracket n is equals to this form. And the proof begins with only the whole number starting from 0 and the positive integers 1 to infinity. So let's first test that when we substitute n equals to 0 here, as well as 0 here. Well, anything to the power, a non-zero value to the power of 0 is 1. So the left-hand side is simply 1. And when we substitute to the right-hand side, well, we have cosine of 0, which is 1, and sine of 0, which is 0. So it is 1 plus 0i. So the left-hand side equals to the right-hand side when n is equals to 0. So this is easy. And now we want to use induction to prove for different values of n, positive n. We first assume that this is true. Cosine theta plus I sine theta k, we just assume that we can simply put the exponent k into this angle for the cosine as well as the sine. And we want to prove this by induction that, hey, if we already have cosine k theta plus I sine k theta, and we want to increase k by 1, so is it are we going to get this formula over here, that this k plus 1 will move into these angles within the cosine as well as the sine. So let's write down that on the left hand side we are going to have cosine theta plus I sine theta bracket k plus 1, and we can of course break this k plus 1 exponent into two parts. One part is k and the other part is 1. So when we multiply, the base is the same, so the exponents add. And well, we are going to take this cosine theta plus I sine theta to the power of k, and we use this assumption. Okay, so we take the assumption and we put it down. And now we are basically opening up the brackets. So all the terms are going to be multiplied with each other. The cosine theta is going to be multiplied by cosine k theta. So that's it, the first term here. Then what about the other term? What about I sine theta and I sine theta? So we have I squared sine theta times sine k theta. So this is the orange term over here. The green term is all the imaginary term, which is I sine theta cos k theta. I sine theta cos k theta, as well as I sine k theta cos theta. I sine k theta cos theta. So we collect the real terms, which is the orange to one side and the green to the other side. Then we use the trigonometric identity to say cos theta plus k theta equals to this expression. So as this identity, sine theta plus k theta equals to this expression over here. And this is what we need. We basically now can collect the theta to be k plus 1 theta and theta plus k theta be k plus 1 theta as required. So it basically shows that this is true. When we are exponentiating by n, we'll get this n, pushing it into the angles within the cosine and sine. Now, this slide only proves that we are doing it for positive values of n. The next slide shows that how we can also say that this is also true when n becomes minus 1, minus 2, and so on. Let's proceed. Right, so let's begin. We have z is still cosine theta plus I sine theta. What is z minus 1? So it's basically z minus 1, as you know, is 1 over z. So we just put z terms at the denominator. Now, we typically don't like things in the denominator to be complex. So to make it real, we multiply by this term's conjugate. So it's cosine theta plus I sine theta, cosine theta minus I sine theta. So this term is the conjugate of this term. But since we are having numerator and the denominator to be the same, so this expression is actually 1. So something multiplied by 1 changes nothing. But what it allows us to do is to deal with the denominator and make him real. So cosine theta times cosine theta is cos squared theta. I sine theta times I sine theta is I squared sine theta. There's a minus sign here. So I squared is minus 1. So this guy becomes plus. So cosine squared theta plus sine squared theta is 1. So the denominator is 1. The numerator, of course, is whatever this is, which is cosine theta minus I sine theta. Alright, so we know that 1 over z is equals to cosine theta minus I sine theta, if the original z is cosine theta plus I sine theta. So actually, by reciprocating, what we get is we are getting the conjugate of z. Now, the other thing to remember is, if we introduce minus theta instead of theta, nothing changed with cosine theta, because cosine theta is equals to cosine of minus theta, since this is cosine, right? This is a cosine graph, and this is theta. So if this is theta and this is minus theta, then nothing changes here. Okay, the same value for cosine. Cosine or positive theta is the same as cosine minus theta. What about sine? Well, sine is a different monster. Sine is an odd function that looks like this. So if this is theta and this is minus theta, this value is equals to the negative, this is y, and this will be negative y. So the sine is an odd function. When we go along the positive axis theta, we get, let's say, positive y until pi over 2. And then if we transverse towards the left-hand side to reach minus theta, we'll also get y, but in the negative y value. Okay, so with that understanding, what we are wanting to do is that we want to introduce theta, and we want to change it to minus theta. And minus theta, of course, get the value negative, so this sign here must be changed to positive, such that this expression is equal to this expression. Now, when we do that, what happened? Hey, if you look at this and you think of this as some variable called this phi, then it's cos phi plus I sine phi. And then isn't this exactly allowing us again to use De Mor's theorem for positive index of n, right? And then we are just inserting n into the index for the cosine and the sine term. So this basically shows that yes, it's true. We can now extend n equals to not only from 0, 1, 2, we also can extend minus 1, minus 2, and then apply the De Mor's theorem. Okay, so with that, that's it. We next will show some example. Thank you.